Today we want to look at differential equations a little bit more. And we're going to pick up where we left off yesterday with Newton's law of heating and cooling. Newton's law says the rate at which an object changes temperature is proportional to the difference between the temperature of the object and the temperature of the surrounding medium. So if y is the temperature of the object, then dy dt is the rate of change of the temperature of the object with respect to time. We're going to set R as the room temperature, the temperature of the surrounding medium, and we're going to assume that R is constant. So there's enough room that when we put the hot cup of coffee in the room, the coffee doesn't have any significant impact on the temperature of the room. And K is the constant of proportionality. C is the arbitrary constant that shows up when we integrate. So C is the arbitrary constant. So those are all the players. What we know is that the differential equation is defining a general solution. So we'll refer to this as the general solution. A differential equation leads to a general solution, and the arbitrary constant will be determined by initial conditions. K is the constant of proportionality. This is going to be dependent in this scenario on how much the object is willing to change its temperature. You know that if you take a metal object and expose it to heat, then it will heat up very quickly. Because metal is okay with changing temperature. You know that if you put a huge pot of water on the stove to boil, it will take a long time for the water to start boiling because the water is resistant to changing temperature. It does not want to change temperature. So we're going to need extra information to figure out what the constant of proportionality is. I'm going to need two different values. But the constant of integration is determined just by the initial conditions. Let's take a look at an example. Actually, let's, we noted that this was a separable equation. Because this is, and it makes sense, this is just a variation on our exponential growth decay that we saw yesterday, where the rate of change is proportional to the value of the function. So we can use our strategy of separate the variables and then integrate. So I'm going to put the y factors on the left with the dy. And I'll put the dt factors on the right with the k. So here we are separating the variables. Note that the separation had to go with multiplication. I need one thing to be multiplied by the dy and another thing to multiply by the dt. So I wouldn't want to separate or distribute the k, because then I have two terms. I have to move things over by multiplication and division so that we can integrate. So we're going to separate and integrate. On the left, we get the natural log of the absolute value of y minus r. And on the right, we get k times t plus c. The integration on both sides produces a constant of integration. And we're going to gather those. So let's actually be more explicit about what we're doing here, since there was a question about it. So integrating on the left will produce a constant of integration, and integrating on the right will produce some other constant of integration. The constants of integration are arbitrary constants based on initial conditions. If you keep them separate and you find out later that C1 is 5 and C2 is 7, that's the same thing as putting C1 over on the C2 side and then finding out that the arbitrary constant is just 2. So what we're going to do, what we do is we gather all the constants of integration. Right now, it doesn't matter what value they are. They're arbitrary. So I'm just going to subtract the C1 from the C2 and get some other constant. So I'm going to have natural log absolute value of y minus r is kt plus some third constant. After we separate and integrate, if it's appropriate, we can try solving for y. Since the natural log of y minus r is kt plus c, that means that y minus r is e to the kt plus c. It's inconvenient to have the plus C3 as a term in the exponent. So we do some algebraic shenanigans. E to the C3 is just some other arbitrary constant. So I'm just going to give it the name C. So rather than have this expression e to the C3, I'll just write it as some constant C. And that's going to be a better place for our constant to be. Now all we have to do is add r to both sides, and we get our general solution. based on what we know this solution should look like, if we're using this equation to model an object heating up or cooling off, if we're using this as a model to see if, as a model for an object heating up or cooling off, that tells us that K is going to be negative because we're going to be approaching a horizontal asymptote of R. Depending on the value, whether the object is heating up or cooling off, that'll determine if C is negative or positive. If the object is heating up, then the temperature of the object is lower than room temperature. So we're going to start off with C being negative. If the object is cooling off, then C will be positive because we'll start off at R plus C rather than R minus C. But here's our general solution. If we had initial conditions, then we would be able to figure out the arbitrary constant C. If we had an additional piece of information, the temperature of the object after a certain amount of time in the medium, then we will be able to figure out the value of K. So C is the constant of integration. That will depend on the initial conditions as usual, but K will depend on how the object heats up or cools off. Any questions? Let's take a look at an example. "20 is room temperature, right? In Celsius. 30 is hot, 20 is nice, 10 is cold, 0 is ice. Having grown up in the Bay Area, you don't really have you have a very narrow temperature band. I don't know about you, but I grew up in the Bay Area. And that means if it's above 75, I think it's hot. If it's below 65, it's cold. And that's it. That's my habitable zone. 65 to 75. Because I grew up in the Bay Area on the coast, like Montara, Moss Beach, that means I just have a preference for lower temperature. So if it's below 65, I consider it to be cold, but that's okay. Above 75, I consider it to be hot, and this is intolerable. So I think if you are more East Bay, but still kind of in the habitable zone, then 65 is cold, below that is intolerable, and then above 75 is all right. I went to school in the valley, and this is just too strange. You go to, I went to school in the valley, and we would get out of the water when it was dark, and it would be like negative 1,000 degrees, and we would be freezing. Then the sun would come up, and by the time we got back and we were putting the boats away, it was like 90. And I go, this is stupid. How, I mean, I wish my oven would change temperature like this, like in the course of one activity. It would be preheated. But anyway, that's all beside the point. I'm pretty sure this is high enough to be ridiculously hot. And that would be coffee that I place in the room. There's also the tolerable temperature for coffee, right? when they first hand you the coffee, it is too hot to drink. It's just ridiculous. It's like, well, why you make the coffee so hot? We had a whole lawsuit about this. People got hurt. But then you gotta wait for the coffee to cool down. Then it gets to like the drinkable zone. And then I don't know what happens, but it's like it speeds up. And I'm like, oh, Newton, you were wrong. The coffee is cooling down faster. Because if you ignore the coffee for too long, then you come back and the coffee is like close to room temperature, it's disgusting. It's like, oh, this is nasty. It's not like I stopped drinking it, right? I mean, addict's gonna addict. It's not like I stopped drinking the coffee, but I'm like, oh, this is terrible. Drink. But then if you take it too far, like put ice in it, then it becomes good again. Like soda doesn't have that. Soda has to be very cold, otherwise it's just nasty. I'll see people go into the fridge, they grab a soda. I go, dude, I just put that in there. It's not cold yet. And they're like, oh, no, it's fine. They open it and start drinking it. I will kick them out of my house. Michael, you think I'm going to tolerate that disgusting behavior in my house, drinking a warm soda? Get out. What's wrong with you? I'm just kidding. I don't like actually kick them out of the house. But they're on the list. I really think twice about, God, do I want this guy up here? I go, why? What did he do? Drank warm soda. And then people think that I'm the weird one. So we have information to build a differential equation, and we have an initial condition. Our initial temperature is 90 degrees. This is our R is 20 degrees. Our temperature at time 0 is 90 degrees. That's our initial condition. The rest of the structure comes from the differential equation. This is the information that we have now. We know this equation is separable and it leads to the solution, the general solution y of t is r plus c e to the k times t. The initial condition says that y of 0 is equal to 90, and that's going to tell us about the value. Oh, well, we have an r. It's been there too long. So in the setup for the problem is where we get the room temperature. Our initial condition is going to let us find what C is, but we need some other piece of information to figure out what K is. How resistant is this coffee to changing temperature? So since we know that y of 0 is equal to 90, then we can see why I wanted that C to be the coefficient. Because that will just be the initial difference in the temperatures. The coffee was initially 70 degrees more than the room temperature. The e to the k times 0 is 1. So this just says c equals c plus 20 is 90. So c is equal to 70. The initial condition told us what c was. And now in the context of this problem, we know what c needs to represent. C is just the initial difference in the temperature of between the temperature of the object and the temperature of the room. In this case, positive 70. To figure out what K is, we will need to know the temperature of the coffee at some other time, because that will tell us how willing the coffee is to change temperature. To find K, we would need the temperature of the coffee at some time after being placed in the room. So for example, if I knew that 15 minutes after being placed in the room, the temperature of the coffee was 60 degrees Celsius. I would attribute the fact that I don't know if 60 degrees Celsius is too hot to drink the coffee. But then I realized it has nothing to do with the fact that the temperature is being measured in Celsius. If you convert 60 degrees Celsius to Fahrenheit, I still don't know if the coffee is drinkable. I know it's not like literally boiling. So that's a plus. But the thing is, I've never measured the temperature of the coffee when I start drinking it, when I find it to be acceptable. So I don't know if it's acceptable yet. But in the context of this problem, we don't really care. 15 minutes after being placed in the room, the coffee was 60 degrees Celsius. So this is a piece of information that tells us, it's going to tell us the K. Y of 15 is 60. And so that means that 60 is equal to 20 plus 70 e to the k times 15. Now all we have to do is solve for k. So we'll take the 60, subtract 20, divide by 70, take the natural log of both sides, bring the 15k down, then divide by the 15. Then wonder, impact the calculator. K is negative. We expected this because we are approaching the asymptote. This is whether we started off with a hot object that is cooling down to 20 or a cold object that is heating up to 20. We got negative 0.0373. Notice that 70, that coefficient, that came exclusively from the initial condition. The negative 0.0373, that came from how the coffee is cooling off in the room. So we needed another piece of information. It makes sense. We had two things that we didn't know, so we needed two pieces of information to find them out. If we had a different cup of coffee and let's say maybe there's like more insulation, so that after 50 minutes, the temperature of the coffee is only down to 80 degrees. That could just mean that there's more insulation in the cup. So rather than getting the cup with the sleeve, you brought your own insulated cup. It's a great idea to keep your coffee hot longer, but it also keeps it in the undrinkable phase longer. Any questions? Yeah. How do you think the natural law the 15 is in front of the K, so it'd be 15K is equal to the 60 minus 20 over 7. Right, so the steps, the in-between, we have 20 plus 70e to the 15K. First, we subtract the 20. And then we divide by the 70. But then when we take the natural log, the 15 is a coefficient. One of these is excessive. And then the fifth, so 15K. And so that's why we divide by the 15. How's that, bro? Okay. The difference between y prime equals k times y minus r is a first order equation, lowercase, not from Star Wars. And if the first order is trying to be the empire again, are they not the first order? I mean, aren't they the second order at least? This goes against the Spaceballs convention. Good is supposed to win because good is dumb. And so you can't have the first order, which is actually the second order, calling itself the first order because now they're dumb. But they're clearly not the good guys because they want to go around blowing up planets. Anyway, lowercase, first order. It's a first order equation because it involves a first derivative. First derivative, your differential equation involves a first derivative, it's a first order equation. When we solved our first order equation, we had one arbitrary constant. It led to one constant of integration. So if I write a differential equation with y double prime, a second derivative, we'll call that a second order equation, and we should expect to find two constants of integration. Let's take a look at a second order equation. I mean, it's going to involve a second. Specifically, I want to look at this second order linear, homogeneous, ordinary differential equation with constant coefficients. As this is math, we got to categorize things. It's not just first order, second order. We got to throw in all the descriptors that we can. And we're going to use our favorite technique for solving problems. We're going to guess. Because that's the only technique we've ever had. How do we figure stuff out? Eventually, it just comes down to we just guess. Not eventually. What's eventually but going in the opposite direction? Like eventually is like a forward in time. What's pre-eventually? What's -1 times eventually? Is there a word for that? Anyway, going back, if you go back far enough, then negative eventually, I guess if we're going back, then that's the event. You just have to indicate the direction. Either way, all math started off with guesses. We just guessed at what would happen, and then we checked to see if it would work. So we're going to solve this equation by guessing. Not just randomly, that would be ridiculous. So we're going to look at this second order equation, and we're going to notice that y prime, and y double prime, since b and c are constant, y prime, and y double prime all have to be like terms. That's our first piece of evidence that we need. Y prime, and y double prime must be like terms, because when I add them all up, B and C are constant. And when I add them up, I end up with 0. So I have to be able to add them together. If y is x cubed, then y prime is x squared, and y double prime is an x. I can't add those things together to come up with 0. So since the sum is 0, these three, this function and its derivatives must be like terms. So that informs us what our guess should be. We need a function whose derivative can be added to the function. So we're going to guess that it's got to be some kind of e to the kt. Because derivative of e to the kt is k e to the kt. I can add those up. And the second derivative is k squared e to the kt. I can add those up. So that's our initial guess. That means y prime is going to be k e to the kt. And y double prime will be k squared e to the kt. We made a guess, and now we're going to check. We don't know what the value of k is. We know the form of the function based on our guess. So I'm just going to plug my y prime, and y double prime into my equation. This gives me k squared e to the kt plus b times k e to the kt plus c times e to the kt. We're trying to figure out the values of k that will make this guess work. Notice that the three terms, we're adding them all up to 0. We have like terms with this e to the kt. So let's factor out the e to the kt. And now we find the conditions under which our guess will give us a solution. E to the kt is never equal to 0. So it must be that the k squared plus bk plus c is where the equal to 0 part shows up. This is the characteristic polynomial for this differential equation. The zeros of the characteristic polynomial will tell us the values of k so that e to the kt is a solution. Notice that for our second order equation, we had a quadratic characteristic polynomial, and so it's going to have two solutions. quadratic, there are two values of k for which we get a solution. We should note something. Since we ended up with this quadratic, that means we're going to have two values of k, but there are different cases. There are different things that could happen. There could be distinct real zeros, plus or minus the square root of b squared minus 4ac over 2a. It could be that we get a repeated real zero, where the b squared minus 4ac part is 0. So we get a repeated real zero. Or we could get complex zeros. If b and c are both real numbers, then the complex zeros will come in conjugate pairs. Not conjugate. If we have a polynomial with real coefficients, then the complex zeros will come in conjugate pairs, a plus or minus bi. So we need reactions to all three of these cases. What happens if there are distinct real zeros? What's the general solution look like? What happens if it's a repeated real zero? What's the general solution look like? What happens if we have complex conjugate zeros? What's the general solution look like? All right, that's going to do it for today. I'll see you all on tomorrow. Everybody have a good day, and thanks for playing.